Now here's a little extra and a little preview. When x doubles, then if we call this x1 and we call this x2, and it wouldn't hurt to write that 2 a little more clearly. Yeah, don't know that that was any clearer. Let's see if I can clean that off a little bit and, oh man, make a decent 2 here. Okay, so if x doubles between x1 and x2, then x2 is twice as big as x1. So if I divide x2 by x1, x1 goes into it once, twice. So that x2 over x1, the ratio of the x values is 2. So we're just expressing by the fact that x2 over x1 equals 2 that x is doubling as we go from point 1 to point 2. Now, if y1 and y2 are the corresponding values of the time between counts in this case, then at least for this graph down here, y2 over y1 is going to be 1.32. So when x2 over x1 is 2, that is when x doubles, the y factor is about 1.32. That means that the y2, this divided by the y1, or this 0.7 divided by the 0.53, is about 1.32. Now, if that's the case, then there's an equation, and we'll talk about where this equation comes from. But we're simply saying that, okay, this means that y2 over y1 is always some power of x2 over x1. So y2 over y1 is x2 over x1 to some power. And if that's the case, then since x2 over x1 equals 2, whenever y2 over y1 is 1.32, or vice versa, when the y ratio of 1.32 is associated with the x ratio of 2, then that ratio has to equal 2 raised to that power. Now, from this equation where we have just a couple of numbers and one unknown p, turns out we can solve for p. Now, if you've had just geometry in Algebra 1, you probably don't know how to solve this equation for p. Even if you've had Algebra 2, and you might have a vague recollection of how to solve an equation. It's an exponential equation. You solve it by taking the logarithm of both sides, or by whatever trick they teach you to trick the SOL into thinking you understand how to solve the equation. But the solution would come out p approximately equal to 0.4. Okay, and this means, well, we'll see what that means. Just wanted to show you that equation. If you understand a little bit about logarithms, you understand that if we take the logarithm of both sides, we get the log of 1.32 equals p times the log of 2. And then that becomes really easy to solve. P is going to be log of 1.32, excuse me, divided by the log of 2. And that's a calculation you can easily do with your calculator, and it would be appropriate to use your calculator to do that equation. But then that would spit out p equals 0.4. So the algebra that goes along with the geometry of this situation, this is really a geometric argument over here related to the graph. But the algebra that goes along with that is a little beyond Algebra 1. It's actually, well into Algebra 2, but it's not excruciatingly difficult. Okay, the other comment I'll make, just one separate comment, is that if you graph this backwards, where you do the length here and the time between counts here, and actually I think I've mislabeled that. Let me stop and fix that. Okay, I wrote this down as kind of an afterthought when I was doing this in class, and I didn't label it correctly. What somebody did on their graph was they did the 1 minute count versus the length. And I realize that I've had the camera a little bit low here. But I labeled this incorrectly. We have the 1 minute count versus the length, and that's what this graph represents, not the length versus the time between counts. That would be an inverse graph, and we're going to see that pretty soon. We just reverse the coordinates and we get what's called the inverse graph, and that has some important relationships. But anyhow, if we do the 1 minute count versus the length, the graph looks like this. If we do the time between counts versus the length, the graph looks like this. And this graph has the power function characteristic, it turns out. If we double the value of y, we're going to get the same ratio, or double the value of x, we're going to have the same ratio for y, no matter what two doubling x values we happen to use. However, this graph doesn't go through the origin. It's going to turn out to have a vertical asymptote, and that requires a little more discussion than we want to go into right now. We want to get this general scheme down. So that's all I'm going to say about that at the moment. But once we really understand this scheme, we'll go on and talk about some of these other things.